Hi, welcome to my presentation. My name is Masa. I'm a PhD student at CPSS Lab in Virginia Tech, and here is the name of my colleagues who made this work possible. I'm going to talk about Spotr, which is a GPS spoofing detection via device fingerprinting today. We have known for long that GPS can be spoofed, and what has been known as a theoretical fact is now being demonstrated in practice quite frequently, like what happened in Russia in 2017. More than 20 ships reported that their GPS system was off up to 20 miles. And there are more demonstrations, but this one is the most recent one. And the reason that we observe this type of attack quite often is that the cost for crafting such attacks is low in terms of both hardware and software. GPS is one of the many implementations of global navigation satellite systems, or GNSS, that are listed here. However, it is the most prominent one, and it is unauthenticated. A general GNSS system has three segments. It has the space segment, which includes the satellites that transmit positioning and timing data to the GNSS receivers. It has the control segment, which is on Earth and monitors the GNSS continuously, tracks satellites and updates the positions of each, and enables information communication on Earth between the satellites and the control system. Also the user segment, where the users, which could be a car, a phone, or even an airplane, use the data received from the satellites for geolocation and timing. GPS is originally a CDMA system, and there are different implementations of it, among which we will focus on the civilian GPS on L-band, which basically lacks authentication, unlike the military one. We are interested in two signals that pertain to the civilian GPS, the CA code and the nav messages. The CA code includes PRNs, or basically the pseudo-random codes that are used for differentiating between satellites, so that we can decode the signal that is received from the satellites and extract the nav messages. And these nav messages can be used for geolocation and timing later on. This is the general block diagram of a GPS receiver. As we can see, it has, in the beginning, it has the RF front end. The RF front end is responsible for capturing the the signals and conditioning them in a way that they can be understandable for the digital section. The digital section includes acquisition and tracking first, which have similar responsibilities, that is, estimating and recovering for the code phase and the carrier of the signal, and also performing the Doppler estimation. The output of the tracking block then includes the nav messages, which go to the PVT estimator. PVT estimator gives a solution for position, velocity, and time through a method which is called the multilateration, and it needs 4 satellites in order to give a complete solution. But the bigger question is, why are we able to spoof GPS? The reason for this is lack of authentication in GPS. Also, the fact that the receivers in GPS are trusting in nature in a way that they assume that the environment is benign. Also, GPS receivers, because of the automatic gain control or AGC implementation, they favor the strongest signal. And this basically opens the way for hackers or attackers to be able to send a signal which has slightly higher power than the authentic one, and this way, thanks to the AGC, they can suppress the authentic signal and take control of the target receiver. Which brings us to the attack model that we are dealing with, which is where it has the objective, the attacker that we are dealing with has the objective of inducing a different position, velocity, and time in a civilian GPS receiver. There are different attack types, like the spoofing attacker, where the attacker is able to craft digitally valid GPS signals and is able to have a receiver locked to its signal. There is a more sophisticated attack, which is the replay attack, where the attacker is basically recording genuine GPS traces and replacing them to the victim receiver. It is able to replicate the subtle intrinsic features of the genuine signal, and that's why it is more sophisticated and harder to detect. This type of attack is referred to as seamless takeover attack in literature, and the figure is borrowed from Radio Navigation Lab of UT Austin, where they demonstrate in southern part of Italy that they can use this type of attack to change the course of a yacht successfully. There are different countermeasures available in literature, like hardware-specific ones where which require usually a large space. They require multiple receivers, and they are very expensive to implement. There are cryptographic-based solutions which are they are also expensive because they require modifications to the space segment side. They induce a big amount of delay to the system, and they are expensive. Multi-system, multi-frequency solutions which consume the military dedicated band, and they are not efficient. However, there's another round of solutions which are called physical layer approaches, where there are numerous ones demonstrated in literature. They try to find anomalies in the receiver observables or the characteristics of the RF signal in order to be able to detect an attack. What they have in common in terms of drawbacks is that they are all sensitive to multipath, they are vulnerable to seamless takeover attacks, and they are all easily imitable. The most recent contribution to this problem is SPRI, which was presented in Mobicom 2016, which shares some of the drawbacks mentioned earlier for the physical layer approaches, but it also relies on presence of the authentic signal in order to perform well, and it needs the digital information in the nav messages, so basically the content of the nav messages in order to function properly. We propose, however, a physical layer-based approach. We propose PLI for securing GPS, where a unique fingerprint is defined for each satellite, which depends on the unintentional randomness in the circuitry of the satellites at basically the manufacturing stage. The uniqueness is because of these hardware imperfections and basically the traces of these imperfections that are left in the analog signaling. That's why the fingerprints are unique and they are not imitable by an attacker. We use PLI because it is effective even in case of multiple attackers, and it is the best defense solution in a resource-constrained environment. PLI has 3 steps of data acquisition, feature extraction, and decision-making. And data acquisition is basically converting the analog signal into digital samples. Feature extraction is the process of defining unique fingerprints for each hardware. And these fingerprints are because of the unintentional randomness in the manufacturing process of the hardware. And this is basically the underlying basis for PLI-based approaches. And decision-making process is defining a threshold based on proximity of the legitimate and malicious features and trying to maximize their separability in a training test process. The decision-making is further classified into classification-based approaches and identification-based approaches, where we choose identification-based approach because the classification one lacks the rejection criteria. Of all of these steps, feature extraction is the most essential and important one because we need to have strong features that are reliable and they are able to create the separability and perform the detection that we are looking for. So here is the definition of what a strong feature is. A strong feature should be lightweight, it should be reliable, and it should be robust to environmental variations and aging. It should be easy to generate, and it should be resilient to attacks. So in other words, it should be inimitable. So how do we apply a PLI to the GPS satellites? This is the general overview of defense when we use PLI for securing a physical, cyber-physical system. And in order to start this process, we need to first find a way to define the fingerprints. But looking into the general GPS receiver, where can we find the features that we are looking for? There are so many possibilities, and we need to find the proper observation point. And basically here is where the research starts. After digging into the GPS receiver, we figured out that the tracking block is the most interesting one in terms of finding a proper observation point for our research. You can see that the tracking block includes the DLL-PLL loop, which are basically the delay lock loop and a phase lock loop. They are responsible for tracking the differences between the time of reception and broadcasting of the signals, and basically estimating their time and frequency misalignment and compensating for them. Within that block, we can see the outputs of the early prompt and late correlator outputs, which are the interesting points of observation. These correlators are matching filters that show a large real part and low imaginary part when there is actually a lock to the system. The figure on the right shows the output when there is a lock, and basically we look into the signal and we segregate the high and low of the real part of the early prompt and late correlator outputs, and this is how we define 6-dimensional features, which are referred to as features 1 to 6 hereafter. But the bigger question is like why these features work. The reason these features are strong and reliable is because of the automatic gain control system, which is found in most GPS receivers. And you can see it here in the block. AGC is a feedback loop that is targeting to keep the distribution of the input signal to the ADC block consistent using a variable gain amplifier that you can see on the left of the lower figure, or the VGA. That being said, we have finalized the design specifications, and so here is what we need in terms of software in order to do data collection. We use GNSS SDR as our main software for collecting GPS traces, and we use GPS SDR SIM for creating digitally valid GPS data. And we use this website for finding the visible satellites at the time of data collection. In terms of hardware, you can see the hardware setup that we put together using USRPs here. And this is how we collect genuine GPS traces, genuine data for GPS. And then we have the spoofing setup where we have a B210, which is the green circuit for basically replaying the data to the receiver, which is the X300. This spoofing is performed in a wired scenario because wireless transmission was not legal in our region. But from one perspective, this is even more generous for the attacker because we are not, because the imperfections of the new channel for the communication are not there yet. So it's basically the attacker is able to mimic the genuine signal even more perfectly. Here is the list of the genuine data sets that we have. Our data is, we call our data sets SatGrid, and we also use TextPad data, that is a repository of spoofing GPS traces, and also the clean data from Radio Navigation Lab. The data that we collect is within the window of 1.5 years, and we have different conditions in terms of rich multipath and no multipath. And we collect data at different locations in the US, including Texas, Blacksburg, Missouri, and Arlington. We also have the spoofing data where we attempt to spoof the genuine data in both dimensions of time and position, or both, and we have different power levels for the attacker because we did not want to limit it to one scenario. To look into the data, the first step is to pre-process the data by outlier rejection. We use the code lock test and carrier lock test, and we remove the outliers to make clean data for further processing. And we go to the final step for designing Spotr, which is a training and testing based approach where we fit the 6-dimensional features that we introduced earlier into a distribution named multivariate normal distribution. And we use the MVN scores in order to make a decision once a GPS signal is being received based on the value of this score to make a judgment if the signal is legitimate or if it is a spoofing data. In the figure, you can see features 1 and 2 for both genuine and spoofed data, and here is the equation about which mathematically represents this type of distribution. However, the data that we are dealing with is noisy data, and in order to compensate for this and generate strong features, we use multiple, with longer duration of observation, which we show here as multiple sample points, or N. This is the summary of Spotr in a block diagram, and but we need to evaluate Spotr in different and in terms of its stability for different positions of satellites for the time of the day with respect to weather, also aging. And we also want to answer the question of what is the sufficient duration of observation for Spotr to function properly, and how long does it last for it to detect the strongest attack available. We have a big cross-validation table here where we try to go over different scenarios by training on one and testing on the other, where we report the false positive and false negative rates on the columns on the right, and we have the number of sample points of observations that are needed for achieving these low error rates. So the cross-validation is in terms of location, time, in terms of presence or absence of multipaths, the types of attacks that are being performed, also the hardware platform that is being used. I try to break this into multiple slides in the following, where I go over the cross-validations one by one. In this one, you can see that training is done in Virginia, but the testing is in Missouri, and we have very low false positive and false negatives, which means that the features are stable with respect to location, and we are able to fingerprint the satellites regardless of the location where the fingerprinting is happening. So the fingerprinter is basically collecting data. We repeat the same process for time, where if you look into the figure on the left, the training is on 2018, but we have testing even in a window of a year after, in September 2019, and yet we are able to have low error rates, which shows the stability of the features with respect to time. We repeat the same for multipath, where we train on the rich multipath data and we test on no multipath, and we do the opposite, and yet the error rates are low, which validates the strongness of the features. We cross-validate with respect to the type of attack in terms of position and time, and the error rates are acceptable. They have low error rates, and where the dimension of the attack is changing from time to position, or both. Finally, the cross-validation is on hardware, but this time we can see that the figure above is showing our setup, but the figure below shows the TextPad, basically the hardware platform that was used for generating the TextPad data using the UT Austin group. But the false positive rate that is shown here is very high. So this indicates that this method is limited to the hardware, and training needs to be done based on the hardware platform that is being used. This is a general drawback of using hardware fingerprinting for securing, which means that even like if the platforms are identical, they need to be trained individually, and it basically validates validates the fact that the fingerprints are varying with respect to the hardware platform. I'll skip this slide, which just summarizes how we use k-fold cross-validation for reporting all the errors. And I will finish the presentation by mentioning the strong points of Spotr. It is, for Spotr to function properly, only one channel of observation is sufficient. It is low in complexity. It is able to detect the strongest spoofing attacks available in literature, discovers the seamless takeover attack, and the replay attacker that we introduce in a power matched scenario. And we elaborate more on this in the manuscript. And the next strong point of Spotr is that it doesn't need channel modeling or estimation. It doesn't rely on the content of the nav message. It is able to detect coordinated attacks where the number of adversarial parties is more than one. And it is purely passive, meaning that it doesn't need hardware or protocol level modifications. And it is robust to environmental variations such as weather conditions or time, and it is robust to multipath. For the weak points of Spotr, our analysis demonstrates that 47 seconds of continuous spoofing is required before an alarm rings. So basically it takes 47 seconds for Spotr to be able to detect an attack, but the attacker that we are dealing with is able to estimate and compensate for channel conditions. It is able to generate match power signals, and these are not easy to be achieved in practice. So in other words, we are being very generous to the attacker, and this is a very strong attacker. The other big point is that the fingerprinter must be individually and securely trained prior to deployment. So basically, first, Spotr needs to be trained on each hardware at the manufacturing stage, and this is a common drawback to all of the device fingerprinting approaches. And that finishes my presentation, and I'll be available if you have any questions. Thank you.